Hi guys, today we will we will study the equation of the beam. Um, the beam equation. You are very familiar with the beam equation, which represents one of the most important topics in structural mechanics. But now we will add we will put an additional term, which is the inertia, which we have neglected in all our previous investigations. You are familiar with the beam equation, right? We will try to add the additional term. We are studying the transverse vibrations of a beam. Of a beam means that it's a structure element where the contribution of the bending moment cannot be neglected, as it happened in the string. So let us consider an infinitesimal element of a beam, which is subjected to, and let us v of xt, where x is the abscissa spanning the dominium, the length of the beam, and d is time. So the infinitesimal element of the beam is characterized by a mass density rho, and the inertial forces will then be rho dx, which is the total mass of the element. We will assume that the deformation of the beam is very small. Sorry. So the ds is approximately equal to dx. Okay. So rho dx is equal to the acceleration of the center of mass of this element, which is the double derivative of v with respect to time. Okay. Now the equilibrium, we put the shear forces v V can change from one side, from the left to the right side, so it's V plus dV over dx times dx. Okay. Okay. If we write equilibrium, and then we have the bending moment m, and then m plus dm over dx times dx. We write the vertical equilibrium, so we have minus v plus v plus dv dx dx. We assume that there is a constant load. Let us call us p. So p plus p dx is equal to rho dx, double derivative of v with respect to time. If we simplify the expression, we divide by dx, we have dv over dx plus p is equal to rho d squared v over dt squared. We know from the rotational equilibrium of this element if we neglect the contribution, the rotational contribution of this element, here we have the shear forces. We have Let us assume that it is the center of rotation. B plus dv over dx times dx, which is the level r, is equal to minus m plus m dm plus dm over dx dx. Okay. So this is too small. Is dx squared, so we neglect it, and the equation yield the following, that is b is equal to dm over dx. We also know that. So we plug this equation inside, and we have the double derivative of the bending moment over dx squared plus p is equal to rho the double derivative of b with respect to time. But we do know the constitutive equation of the beam, which is m this constitutive equation. Sorry, I'll come in a second. It's too hot here. Okay. So this is the constitutive equation. It comes from the Euler-Bernoulli hypothesis. The hypothesis is that the cross section of the beam, which are initially perpendicular to the beam, remains perpendicular to the neutral axis of the beam. There is no shear deformation, how it happens in the Timoshenko beam. So this is the first great assumption of this equation, the Euler-Bernoulli equation. The sections remain plane and they remain orthogonal to the neutral axis of the deformed beam. Okay. So if we plug this equation inside, we will have the double derivative of v over the fourth derivative of v over dx fourth plus p equal to rho dv squared. Okay. This is dynamic beam equation, indefinite. It's a fourth order partial differential equation. See, if we consider the homogeneous equation, so we assume that there is no load, no external load, the equation becomes I forgot A. A stands outside if it's constant, because we had d square dx square of right? heat is constant, it goes outside, and we have this equation. So the double derivative of v over dx4 times AE is equal to rho dv over dt. If we divide, this is definitely not the wave equation, because we have a fourth derivative, not a second derivative, a fourth derivative. And I will show you why this is not representative of a wave equation. Let us divide by AE. We call A square A over rho. So it becomes 1 over A square. Okay. We discussed about the dispersive nature of elastic medium, but now we can see. Let us consider, let's see if a wave can propagate inside this medium, and which is the relationship between the phase velocity, c, and the wave number, which we know it's called dispersion curve. We consider that a wave which has this form, v of x t, is a e to I omega gamma x minus omega t. We saw that this is a wave propagating in a certain direction inside that beam, gamma x minus omega t. We know that it's a wave because the x must increase linearly. If x increases linearly, then t must increase linearly to have the same argument of this expression, so to have the same amplitude of this perturbation. So the perturbation to moves constantly with a certain velocity. The velocity is equal to omega over gamma. This is the velocity of propagation of the wave. So if the velocity is constant, so x must increase and t has to increase too, to have the same value of the propagation at increasing time and increasing displacement values. So if we substitute this equation, we impose that a wave propagates inside this equation. So it's a gamma to the fourth derivative, because the derivation, and then we have a to the I and then we have 1 over a square, and then the derivative, which is omega square, and then the same term. We can cancel both terms, and then we have gamma to the derivative. We know that c is the phase velocity, omega over gamma. And we also know that a square is e over rho. divide by omega square both terms, no, divide by gamma square both terms, we will have c square. This is c square. So it is square, so we have gamma square is equal to c square over a square. So c square is equal to square over square. So c is a times gamma. A times gamma, yeah. This is important. A times gamma. This is a dispersion curve of a beam. So if a wave wants to propagate inside the beam with a certain velocity, which is omega divided by gamma, that velocity is not constant and depends on the wave number. I remind you, the wave number is the number of oscillation of that wave per unit of length. Per unit of length. Okay. So if there is a wave number 1, you see the wavelength is 1 meter. It is gamma 2, the wavelength is a half meter. Because we would have 2 oscillation to complete oscillation in 1 meter. Okay. This concept is a specular to that of a frequency. The frequency is the number of oscillation in the time is the number of oscillation per unit of time. So how many oscillations we have in 1 second? Here is the per unit of length. How many oscillations we have per unit of length? So if the wave number is almost zero, what does it mean? The wavelength is very large. I mean, we are considering big waves with very, very long wavelengths. Their propagation is zero. It's almost zero. They are very slow. Inside, when we go to higher wave numbers, so the number of cycles per unit of length increases, we will have increasing velocities. If the wave number is infinity, the velocity is infinity. This is dispersion law, which means that if we have a pulse or a perturbation, see, propagating inside the beam, that perturbation will have a distortion. Because the harmonics which compose this peculiar shape, this peculiar perturbation, each one goes with their own velocity. So the shape of the distortion will change, and we have the dispersion, the dispersion phenomenon. The word distortion is very common when talking about signals in cables or in the era of internet, you want that signals, the information propagate without distortion, meaning that we don't want that there is any loss of information when the information, which is the signal, travels from one point to another point. But every medium has some distortion features, dispersive features, which means that we always lost some information when the fact is, uh, um, if that information that we lose is valuable or not. The beam is the mechanical example of a dispersive, a highly dispersive medium. But do waves in a beam actually behave like this? This is actually the dispersion curve of a beam. Well, this is an Euler-Bernoulli beam, so we have many assumptions. Namely, we have, as I said, the cross-section remain plane and orthogonal to the neutral axis of the beam. Then we are neglecting the contribution of so we are neglecting the contribution of shear. But there is even another contribution that we are losing, which is when you consider the kinetic energy of an element, which is the kinetic energy is 1/2 v squared. dm is the element of mass v squared, which is the velocity. We are considering just the contribution of the vertical displacement. We are neglecting the rotary kinetic contribution, which is 1/2 dm. We can call r d theta squared, where r is the radius of rotation of that element of the beam, and d theta is the angle. So when theta is very small, we can neglect in the kinetic energy the contribution of rotation. Otherwise, it becomes far more important, and the Euler-Bernoulli equation does not fit the experimental data. So in reality, the beam behave like this. I will be more. This is the beam, the Euler-Bernoulli beam. This is the Timoshenko beam. This is the Rayleigh beam. The Timoshenko beam considers the contribution of gamma, which is dV over dx, I mean the shear strain. And Rayleigh considers the contribution of the rotation. So it is not true that as the wave number grows, the velocity tends to infinity, but after a certain wave number, the velocity is constant. Depends on the elastic properties of the beam, but it remains constant. It cannot go, the propagation, the information, the pulse cannot go with a higher velocity than this one. In fact, the experimental points like this one. If we had to put some dots corresponding to experiments in that graph. So that's how things happen in reality. The beam is a highly dispersive medium. Euler-Bernoulli tries to simulate, to grasp the dispersive behavior when we are dealing with low wave numbers. But when we go to higher frequency waves, the Euler-Bernoulli hypothesis do not stand, and we must model the beam using the Timoshenko and the Rayleigh beam. Okay, I hope it is clear. Ca times gamma. This is the dispersion curve of a beam. The velocity, the phase velocity, or the velocity of propagation of a bending wave is not constant, but it increases linearly with the wave number. Now we will try to solve the problem a very common beam. You have studied tons of time. The pin beam. Okay. And it's more the talk. So the governing equation is as we have done in previous times. Sorry, the phone. Previous times we have the v of xt can be written as the product of two terms, one depending on just the x, we call it x of x, and then just depending on t. This is the method of variable separation. Variable separation. If we plug this inside the equation, we will have x4. I cannot go on by writing the partial derivatives because it's too much time hassle. Times t is equal to 1 over a squared, the second derivative x times the second derivative of t. If we divide by xt and xt both terms, we will have this, which is x, the fourth derivative of x divided by x is equal to t, the second derivative of t divided by t, times 1 over a squared. How can this one be equal? I mean, this one depends just on x. This one depends on t. So the only condition where the two terms are equal is that the two terms are equal to a constant, and that constant. So here we have the x. Here we have the t. So we can call the constant beta squared. Okay. So the main advantage of writing with the method of variable separation that we have the fourth order partial derivative equation, and now we have an ordinary differential equation, namely two ordinary differential equations. The first is this one. And the second one is this one. We can write them differently. So the solution of this equation, which is the function that derivated 4 times, remains the same, is the sine and cosine, but there are even other 2 functions which remain the same. There are the hyperbolic cosine and the hyperbolic sine. So the total solution is x of x is and then we have t, which is always the same. The constant of the x of x of the displacement term derived from the boundary conditions. The constant of the time-dependent term derived from the initial conditions. It is also named the initial value problem and the boundary value problem. Now we will forget about the initial condition problem and we'll focus on solving the boundary value problem on a simple case, on a few simple cases. So we are solving x of x, we're writing a sine of beta x plus b cosine of beta x plus c sine hyperbolic of beta x plus d cosine hyperbolic of beta x. And let's consider a pinned beam. So which are the boundary conditions? The displacement is 0, so x of 0 is 0, and the moment is 0, so the second derivative is 0. And the same stands here, so if L is the length of the beam, we have x of L equals to 0, and the double derivative of x in L is equal to 0. So if we make all this, so x in 0, let's start solving it. So x in 0, or what? And then we make the double derivative. Just one term remains in the equation. Is the sine. Actually, this is the only condition that remains. Because using the others, we will have that d is equal to c is equal to d and is equal to 0. So only a is different than 0, and we will have the characteristic equation by imposing these conditions, which are a sine of beta L is equal to 0, which is the characteristic equation. We discussed about this term. Characteristic means that using this equation we can find the eigenvalue problem. This is the sort of eigenvalue problem. So which are the conditions where the argument of the sine is 0? It means that the argument beta L is equal to n pi. but we know beta n because we have infinite solutions, beta n. So when beta n is equal to 1, we have this shape, the sine of pi L over x. If beta n is equal to 2, when n is equal to 1. When n is equal to 2, we have sine of 2 pi times x, and so on. We have symmetric, antisymmetric, symmetric, antisymmetric waves, where at the point where the wave does not shape, and there is a sort of specularity between wave and mode. The points where this function does not move are called nodes. The points where the function moves the most, when attain the higher values, they are called antinodes. Symmetric, antisymmetric, symmetric, antisymmetric. There is an alternance between symmetric and antisymmetric functions. These are called eigenfunctions or mode shapes, because as we see, if these are the solution, the dynamic of the beam can be written as a combination of, as a summation of all the solutions of that equation, and for example, in the plane beam, by summing up all this term with their coefficient, which depends on the time of the initial value problem. So we solve the initial value problem, and we will find the coefficient. So the total solution would be b of x t is the summation e equals to 1 over infinity with some terms which depend on t times, in our case, x of x is sine of n pi x over L. Let's call it n. Okay. So the response of a beam can be written like this. Is the contribution of all sine terms. However, each function has its own frequency of vibration, its peculiar pulsation. I mean, this one goes up and down with a certain frequency. This goes up and down with another frequency, and which is the relation between the frequency of vibration and the wave number. We wrote before that, let me remember, omega square over a square is equal to beta square. Okay? So omega square is a square beta square. And so omega is a beta square. Omega is a beta square. So omega is 2 pi f. 2 pi f is a beta square. So f is a beta square means n pi over L square divided by 2 pi, 1 over 2 pi. If we rearrange this expression, this f is equal to a times n square p square L square times 1 over 2 pi. So we have pi and pi. So it becomes a, which is a over rho, So N squared pi over L squared times 2. I will write it bigger. This is very famous. This is the expression of the frequency of vibration of a simply supported beam, of a pinned beam. Very important, very important, very important. We will find in the standards, for instance, if we want to start the vibration of the floors, you will find this equation. So these are the mode shapes, and this is the corresponding these are the corresponding natural frequencies of these mode shapes. Very important expression that we derived here. This is the simplest case, which and we can find the solution of this very simple case directly by solving the 4 algebraic equations which represent the boundary conditions. But we are in more complicated cases. Let us consider another case. I forgot. We do not need to cancel A, B, C hyperbolic sine of beta x plus D hyperbolic cosine of beta x. So let's consider a free beam. So we have the bending moment and shear that are 0. So the double derivative in 0 is equal to 0. The third derivative is 0. Well, instead we have the clamped beam. You know the conditions, x of 0, 0, and then the rotation angle is 0. X prime in 0 is equal to 0. X of L is equal to 0. X prime in L is equal to 0. And so on. Clamped free, etc. And if we substitute we express these boundary conditions in terms of A, B, C, and D, we find always we can find in these cases just this an equation written like this, and then let's call it differently. It's called a matrix. A certain matrix of coefficient value of constant value times A, B, C, D is equal to 0. But the peculiar thing is that the shape of this equation is inside cosine of beta L, sine of beta L, hyperbolic cosine of beta L. I mean, the unknown are not just this A, B, C, and D. The unknowns are the beta L. Or is the beta or the beta L? But this is customary to consider just beta times L as the unknown, just the product, because it is independent on the length of the beam, because it always happens that we have beta times L always. So we can just estimate the product rather than beta alone. Okay. So how can we solve this problem? Free, clamped, and whatsoever. We can impose the determinant. We don't have a solution, so we must, if we want a solution, we must impose that the row of this system of equations are linearly dependent, and to impose that condition, we can impose that the determinant of this matrix is equal to 0. The determinant of M is equal to 0. This is an equation, a fourth order equation, which is called the characteristic equation. So the characteristic equation derives by setting the coefficient matrix of the system of equations which describe the boundary conditions of this problem equals to 0. And the determinant of M is equal to 0 is called characteristic equation. And to solve it, you just need to solve it numerically, because there are not an analytical solution, there is not an analytical expression of the beta as in the pinned beam. So, in literature, you will find tables like this one. And then once you have found the beta time L, you go back to that system of equation and you find A, B, C, and D. But you know that. You can know that. We have this one. We have this one. We can have this one. Okay, and we have corresponding to each case, we have beta 1L, beta 2L, or beta 3L. We have the solution, the numerical solutions. The tables are like this. I will find a table for you. For instance, if we have here beta 1 times L is equal to 1.8875, 4.694, 10 times 996. What does it mean? It means that the solution of the characteristic equation are these ones when we have a clamped free beam. So if we want to solve the equation and find A, B, C, and D, we just rewrite the boundary conditions and we set that beta times L are equals to these values. And then we find A, B, C, and D by solving the undeterminate system of equations. You can see it, everything, okay? I want to show you another very little thing. We found that the response of a beam can be written as V of xc, the summation of time-dependent terms times other terms, which we call x of n of x, where n goes from 1 to infinity. These are the mode shapes, which depend on the betas, and we know that omega squared divided by a squared is equal to beta 4, and we can derive the natural frequencies from this expression. Right. You studied before in the other part of the course that mode shapes are orthogonal between each other with respect to the matrix or stiffness matrix, to the mass or stiffness matrices. We are considering now are these mode shapes which are not anymore vectors but they are functions, so we call them eigenfunctions. Are these eigenfunctions orthogonal between each other? We are asking this. We will try to demonstrate that in some cases when we have orthogonal, we have homogeneous solution, we have homogeneous boundary conditions, we have orthogonal mode shapes. Let us consider another time we will rewrite the indefinite equilibrium equation of the beam, which reads like this. We know that the solution can be written like this, so we assume that we plug into the equation first a mode shape, which we call x of m of x, and then another mode shape, x of m of x. So if we plug first this one, and we will use the compact notation for derivation, we have the x fourth derivative of n minus x of n divided by a squared is equal to 0. And then we have x of m fourth derivative minus x of m divided by a squared is equal to 0. How can we prove that two modes are orthogonal between each other? The orthogonality conditions is this one. Between two vectors a and b when are orthogonal, when the inner product is 0. With two functions f of x and g of x are orthogonal with their product, and then summation for all x's is equal to 0. Just write the same definition. So we must find if these two modes are orthogonal, and x of n and x of m, then the summation x of n times x of m dx is equal to 0. Is it true? Okay, we multiply both equations by x of m, and the other by x of n. And then we integrate over dx. So we have okay, and then we subtract these terms. Okay. If we move this derivative to this term by applying, x of n 4 times x of n can be written using the sorry for a second, I make a pause.